Hi class. This is an example problem for unit 3.2. In 3.2, it's just a continuation basically of 3.1. Nothing too crazy that's included in this section. So I've taken problem 3-15 from the book, and it looks like this. Where basically we have 3 ropes. We have this rope, and then this, which is, well, I guess a spring. And I've gone ahead and redrawn that up here on the board with the dimensions and everything. But we have these 2 ropes in the spring. We're told that the spring has a spring constant of 800 newtons per meter. We're told that its length is 500 millimeters. We're given these other dimensions, and we're told that the length of the unstretched spring is 200 millimeters. And we're asked to find the tension BD and BC of these 2 ropes. So how do we go about this? Well, the first thing I'm going to start with is just figure out what the force of my spring is. I already have all the information I need to figure out what my spring is, right? The equation for a spring is just the spring constant K times the deflection, which I'm going to represent by this delta. So that is going to equal 800 Newton meters, and the deflection, now I've got to be careful not to mix up my meters and millimeters. My deflection is, so my length now is 0.5 meters, and my unstretched length is 0.2 meters. So that gives me 0.3. When I multiply everything out, what I end up with is a spring force of 240 newtons. Okay, so we got that. Now that I know that, I'm going to go ahead and draw a free-body diagram at point B. Point B is where all my forces of interest are acting. So if I draw that, I get tension BC going that way. I get my tension BD going down that way. And I get my spring force going that way. And for these forces, I can draw the little symbol of triangles. And for this one, it'll be 400, 400. This guy. Well, actually, let me just simplify that. I can do 4 and 4. And for this one, I can do 4 and 3. And luckily, I know just off the top of my head, because I've seen it before, that when you have 3 and a 4, the hypotenuse is 5. For these, my hypotenuse will have a length of squared okay. So I have 2 unknowns, and for this free body diagram, I know this, right? The sum of all my forces in all directions must equal 0. So I can do my sum of forces in X and my sum of forces in Y. I'm going to start with sum of forces in Y. I'm just going to pick, honestly, it doesn't matter in this case. So I'm going to say my sum of my forces in Y equals 0. So 0 is going to equal, when I see force spring isn't in here at all because it's only an X. So I just have to, I'm going to end up with a relationship between TBC and TBD. And so what I'll get is that TBC it's going up, and then it's going to be 4 divided by 2 minus TBD. It is 3/5 using my little similar triangle. And so then when I rearrange this, then I'm going to pull TBD over to the other side and turn these into the decimals. Again, I'm getting that 0.6 TBD equals 0.707 T BC. And when I pull the 0.6 over, I end up getting that, sorry, yeah, sorry. End up getting that T B D equals 0.707 divided by 0.6 TBC. I'm going to hold on to this. This is going to come back in use. So obviously I didn't solve for one, but now I can relate them to each other. There's a fixed relationship between TBD and TBC. And now I'm going to scoot over here so you can actually see what I'm doing. I'm going to use my other equation. Sum of my forces in x equals 0. And so 0, I got a negative F spring, which is 240, so minus 240. And then I got plus T BC 4 square root of 32 plus TBD 4 this. And I can do simplify that one step further, and I get TBC times 0.707 plus TBD times 0.8. And now I'm going to sub in this relationship for one of these values. So I'm going to call this equation 2, and I'm going to say sub 1 into 2, just so I can keep track of where my values are coming from. And when I do that, what I end up with is I'm going to get 240. And I'm going to replace TBC with TBD. So when I do that, I get 0.6 divided by 0.707 times 0.707 TBD plus 0.8 TBD. So by doing that substitution, now this equation only has TBD in it. So you'll be seeing stuff like that a lot where you have to do a little bit of substitution to solve for your unknowns. So now I can solve it no problem. So these points 0.707s cancel out, and I get 240 equals 0.6 plus 0.8 TBD, and I can say that TBD equals 171.43 newtons. And I can call that number 3. It's barely seeing on the screen. Now I'm going to put sub 3 into equation 1, and I get that TBC when we do the math equals 145.48. Right, so I just took this value, plugged it right back into here, and then solve for my last unknown. And those are the forces required to maintain equilibrium. Hopefully that kind of makes sense. How we can use, we can look at any individual point in our system, evaluate all the forces acting on that. We know they have to sum to equal 0. We have, when it's coplanar, we have 2 equations, sum of forces in y and x, that we can use, so we can solve up to 2 unknowns for a given point in our system. And we can do a little bit of substitution in the cases where we can't easily solve them one at a time. So hopefully that makes some sense and gives you some direction and help as you go about trying to solve these problems too.